Our next presenter is Dale Mc Conachie from the University of Michigan. Please join me in welcoming Dale.
Thank you. So I'll be presenting my work on deformable, bandit-based model selection for deformable object manipulation. So deformable object manipulation is important for everything from everyday tasks such as laundry or cooking or things like that, all the way through to medical and industrial applications. So one of the difficult aspects of deformable object manipulation is modeling. Some approaches have used high-fidelity FEM-based models, while other approaches have tried to bypass the modeling entirely by learning from demonstration. In both of these cases, there's a time-intensive training or tuning process that requires a lot of manual engineering, and this is something we're looking to avoid. So our approach is to use a collection of models that are able to represent the task as a whole and learn which task or which model we should use online instead of having to do this modeling a priori. So there's two particular types of models that we will be using in this work, an adaptive deformation Jacobian and a diminishing rigidity Jacobian. Now, all of these, regardless of the high fidelity or the more approximate methods, require tuning parameters. So we're going to look to avoid that tuning offline and learn what to do online. So if you're not familiar with the multi-arm bandit problem, think of it like a slot machine or a set of slot machines. So you want to win the most money, but you don't actually know the reward structure of each slot machine. So the question is, at each time step, which slot machine are you going to use? Which arm are you going to pull? So what you can do is you can try and estimate the reward distributions of each slot machine and then maximize your expected reward as you go through the task. So for example, if you've pulled this arm quite a lot, you might have a good estimate of its reward, and you can exploit that knowledge. However, another arm might perform better if only you knew more. So you need to explore the set of arms, the set of models, to see which one works best now. So this idea has been used for robust trajectory selection in the past in an offline manner. We're looking to do this online for model selection. So in order to define this as a multi-arm bandit problem, we'll need to answer three questions. What's an arm? What does it mean to pull an arm? And what is the reward signal? So we're going to take a look at these three questions for model selection. We'll take a look at three bandit algorithms, two existing, as well as our extension to common filtering for non-stationary multi-arm normal bandits, where we add the D, we make it dependent, as well as our results on both synthetic and simulated experiments. I'd like to stress that both model selection as a multi-arm bandit problem, as well as our multi-arm bandit algorithm, are unique to this paper. So taking a look first at the framework, pretend for a second that this is a real rope with a real gripper. We're going to discretize the rope as a series of points, and then we're going to try and deal with a model that is just a mapping between the changes in the gripper and the changes in this representation, these points. In our case, this is just a Jacobian, but in principle, it could be anything. So what does it mean to pull an arm? To pull an arm is to use the model to at each time step, choose a model to generate and execute a velocity command. So we just need some mapping between a desired movement of the cloth, a P dot, to our gripper configuration, a change in the gripper configuration. In our case, we're going to be solving a minimization problem where we try to match the desired change in the rope or cloth as closely as possible while avoiding things like moving the robot too quickly or collision, overstretching, things like that. For our reward, we're going to base this on the idea of having a task error. So we're doing well if we decrease the task error. We're doing poorly if we increase the task error. We're also introducing the notion of the utility of a model instead of the accuracy of a model. So a model is useful or has high utility if the expected task error, if we use this arm, is high. Or sorry, if the expected reward is high. So if we're going to decrease task error, this is a good model to use. So taking a look at the three multi-arm bandit algorithms, the first is UCB1 normal. This is a very common baseline to compare against, so we're going to use it. It assumes stationary and independent distribution. So that means that the slot machines don't change over time, and pulling an arm on one slot machine doesn't give you any knowledge about the other slot machines. The KF-man-B algorithm assumes non-stationary arms. So that means that the rewards can change over time. If you think about our example domain, very clearly, if we are at 0 task error, then doing anything can have a negative result, whereas if task error is large, we can actually achieve some reward. So clearly, our bandits are non-stationary. However, our bandits are also dependent. If we use one model, we can reasonably expect to get information about similar models. So we want to take advantage of this coupling between models to learn more at each time step. So the way these algorithms work, for UCB1 normal, what we're going to do is we assume we have some distribution, some estimate of the mean utility, and we're going to pick the one that has the highest upper confidence. So which one do we think could possibly perform the best? For KF-man-B, we do a similar approach where we have some estimate. We're going to use Thompson sampling to sample from the distribution, and then pick the model that has the highest sample at that time step. And for KF-man-DB, we're going to do the same thing, except we're going to draw a joint sample from the joint distribution, and once again, pick the one that has the highest reward. So I'm going to take a closer look at the process dynamics themselves. So for our model, we want to encode everything as a linear system with Gaussian noise. So it randomly drifts around is our process model. But the question here is, how do we choose the covariance? That's often the art of common filter tuning. What's our covariance look like? What is the noise model? So what we're going to do is we're going to leverage the similarity between model actions. So if, for example, model I and model J produce a similar action at a given time step, we would expect them to have similar utility. We would expect them to perform similarly. So in the same vein, if two models produce dissimilar actions, one says move the grippers left, the other says move the grippers forward, we would expect them to have low correlation. There's not much information gained between the two. So we're going to take a look at a synthetic system where we evaluated this principle where we actually know all the models. So we set up a strictly linear system where we have underactuated dynamics, and we just add random noise to every element of this Jacobian just to evaluate how well this works in the more general sense than just an identity example. For a model set, so this is our collection of objects that we're going to select between online. We take our true Jacobian, and for each model, we add a different set of random noise. So we end up with 60 different models that are dissimilar from the original by some amount. We're going to start the system at 10, 10, 10, 10, and try and drive it to 0. Our error is just the difference between the origin and where we are. The criteria we're looking at here is total regret. So lower is better. We don't want to regret things. And it's a comparison between the reward of the action we took and the algorithm selected compared to the best action the algorithm could have selected. So we're going to use 1,000 actions per trial. So we're going to command the system 1,000 times. We're going to run 100 trials to evaluate this across a broader range of systems to get some estimate of its performance in general. So if we take a look at the average and standard deviation of total regret, we can say that our algorithm on the left, right, is able to get a much lower total regret compared to the others. In particular, if we look at the very high dimensional cases at the bottom, we're actually much better in general. These are the ones we're interested in as they're representative of our simulated tasks. So we're going to take a look at 3 experiments. The first, winding a rope around a cylinder. The second is spreading a cloth across a table. And the third is a 2-stage coverage task where we try to cover the top of the first cylinder and then the backside of the second cylinder. So we're only going to take a detailed look at the first and last as they provide the most interesting results and discussion points. So let's take a quick look at the experimental setup for all 3 of these. So the deformable object is shown in green, the gripper is shown in blue, and we've discretized the surface of the cylinder as shown with the red points. So the task error is just the distance between the red points and the deformable object. Our desired direction to move the rope is just towards the red points while avoiding overstretch. For our model set, we're going to use 49 diminishing rigidity models with varying parameters and 11 adaptive deformation Jacobians, again with varying parameters. Because 2 of our Bandit methods are stochastic, we're going to run each trial 10 times to get an estimate of how well these perform in general. So if we take a look at the first example here, I'm showing a single model on the right with our method shown on the left. In the top corner is a histogram showing the selection of the model chosen at each time step by our method. So as the task progresses, we can see that our algorithm is exploring the model space using the models uniformly. Eventually, the single model method actually fails entirely and is unable to complete the task, while our method is able to avoid this failure mode and is actually quite successful. If we take a look at the error and total regret plots, we can see this play out again. We have the models that failed. If you take a look, they perform very well at the start of the task and then diverge quite rapidly and never recover. Looking at total regret, we can see that our algorithm is also able to produce total regret. However, in general, these methods all produce very similar error traces across the whole task, showing they're all very competitive for this example. I'll talk about the histograms in a moment for the next example. So in the next example, we're going to show one of the baselines versus our method. One addition I've shown here is the desired direction is shown in green, where we can actually see the direction we're trying to manipulate the cloth at each time step. So as we reach the second cylinder, the method that learns slower gets stuck quite quickly and takes a lot longer to sort of dig its way out of this local minima, while our method is able to wrap all the way around the second cylinder and achieve the task. So if we take a look at the error and regret again here, we can see similar results where all of our Bandit methods are able to solve the task, while the single model methods frequently fail. If we take a look at the regret plots, we again see our Bandit algorithm performing better, with one exception that I'm going to talk about on the dirty laundry slide. You can see that error trace as well. So talking quickly about optimization time, one thing is because we need to compute this model similarity, we take a lot more time to calculate our next action, but that's something we think we can address in the future. So dirty laundry. Our method is doing global planning for single parts of the object and greedy one-step planning for the whole object. What this can lead to is grippers on opposite sides of the object where we try and pull the cloth through the object and we fail at the task. In this case, it looks like the simulator failed. I would call this the failure of our method. So taking a look at some of the conclusions in future work, our formulation naturally avoids some of the local model minima, and we find that exploiting the best model may not be necessary. It's avoiding bad models that's more important. We still need to do some planning, and we're looking into some cheaper estimation methods for model similarity than what we're using right now. So with that, I'll turn it over to you guys for questions. Thank you.
Thanks. How about we start with our respondent, Ronald Derowitz. Where are you? Right there.
Really nice work. I think the problem of dealing with deformable objects in motion planning is really hard, and part of it's the aspect that we don't have good single models to plan around. So what I'm curious about is a little bit more about the dynamics when you add more and more dynamics in these scenarios. So you had the case of essentially like putting this tablecloth over the objects. And another technique that people might use in that circumstance is to take sort of both of the corners, sort of throw it through the air, and then let the whole tablecloth settle on the table rather than dragging it across. And that would require sort of much more of a deeper knowledge of the dynamics. And so what I'm wondering is, with an approach like this, can you sort of run it in a closed loop at faster rates to try to handle those? Or do you need other sorts of extensions to handle those sorts of situations?
So one thing we're doing here is in this work, we're treating the system as quasi-static. It's one of the assumptions we're making that clearly isn't true. So we haven't tried using this in a very dynamical fashion. One of the reasons for that is in order to model dynamics, at this point, we need these higher fidelity models, which are much more computationally intensive. Some of the previous work on this has tried to use simulators and things like that to deal with the dynamics. However, in those examples, it's hours of runtime to do a simple task like that.
So I'm actually wondering, it's natural by the way, but for the Mach Bandit, usually you also have the action because of exploration, right? So I'm wondering, when you say that you associate what's the resulting action that is given as whether the model is better or not, what is the effect of having more exploration, which you will usually see at the beginning of the MND rather than at the end?
So if I'm understanding your question correctly, this sort of addresses these histograms that I didn't speak about in great detail. So if we take...
Coming from your metric, right? You're saying that this model is good if the resulting actions
So the way the metric is working is that we're evaluating, our reward signal is the decrease in error. And so what we're actually doing is we're estimating the expected reward. And so our estimate can have some uncertainty in it, that both because the measurements can be uncertain and because the system can drift over time, particularly as the object moves in and out of contact. And so part of the natural framework of multi-armed bandits is to trade off exploration, exploitation automatically. With this particular method, we don't have any analysis on the bounds on how well we do in general. And so that's something we might want to look to in the future. But right now, this exploration is just a natural part of the way this formulation works. We have, for example, back quite a few slides, right here, we sample from the distribution of our estimate of utility and then pick one of them. So if a model has high variance, it's more likely to be sampled in general than another model.
Yeah, I understand that part, but if you go to the next slide.
So actually, we're running a little late, so I'm going to interrupt this because the talk ran already over and the Q&A is going pretty long. So let's thank speaker again, and let's have the next speaker set up. Gerald, can you come up?